Welcome everyone to today's seminar series. So today we have invited Machine Learning in Geoscience Club to give us a special seminar workshop about what is machine learning and how do we apply machine learning to geoscience in general. So let's start with sharing my screen. And then can everyone see it?
Yes.
Okay, so I will let Heidi, the lead of our Machine Learning in Geoscience Club, to introduce the first few slides.
Okay, so if you want to, next slide real quick. All right, so welcome everyone. I'm really excited to talk to you about machine learning in geoscience, and Grace and myself are founding members of the Machine Learning in Geoscience Club, and we meet weekly to talk about machine learning projects and brainstorm together. So this, I hope, will be informational and fun for everyone to participate in. So we've structured this in 3 different sections, and what it'll be is we'll give an introduction about machine learning in general and how it's been applied to geosciences so far. Then Grace will take over and talk about the general structure of machine learning projects so you can start doing this in your own research. And finally, we'll go through an interactive tutorial of a convolutional neural network to classify different rock images. So what is machine learning? Why should we use it? It's very buzzy. Everyone talks about this. It sometimes seems like it's a black box, some sort of magic that isn't necessarily rooted in statistics or even in reality in some cases. But the truth is that machine learning is a tool, and it's a tool that uses algorithms to identify patterns and or make prediction based on your input data set. So there's 3 sort of umbrella categories that machine learning is particularly well suited for, and that is for the purposes of classification, which is what we'll talk about more in detail today, for regression, but also for clustering. So if you have issues in your research that you're trying to do one of these 3 things, machine learning might be right for you. So some of the advantages of using machine learning. So non-machine learning approaches can be computationally or financially expensive and error prone. Machine learning can handle really high dimensionality, and so it's really well suited if you have high dimensionality data sets like we often do in the geosciences. And it really helps you to find these plausible connections between inputs and outputs. So just to give some examples of novel applications of machine learning in geosciences from the past few years, there's this is a nice summary figure from a Bergen et al. Paper from 2019 that I encourage everyone to read. But this top row is showing an example of an automated approach to mapping lithology. So they're using this remote sensing data and applying a random forest machine learning approach, and what they're getting out of it are lithology labels. So this random forest approach can be really well suited if you have sparse ground truth data, and it gives a robust estimate of the uncertainty of your predicted lithology. And that second row that you see there is showing training a deep neural network, which Grace will go into more detail in section 2 of this talk. And what it's doing is learning a computationally efficient representation of viscoelastic solutions in Earth. So the machine learning approach is allowing for calculations to be done quickly and reliably and with really high spatial and temporal resolutions. And the third row here is showing an example of inversion, where the input is a non-negative least squares reconstruction. So what the network is trained to do is reconstruct a projection into one subspace. So the machine learning approach provides the means to address these inverse problems with sparse data and still obtain pretty good reconstructions. For that example, undersampling is encoded into the training data. So that can be compensated by the generation of low dimensional latent space from which the reconstructions are obtained. And finally, for this example, the fourth row is showing applying a random forest approach to continuous acoustic data. The purpose of that being to extract fault friction and bound fault failure time. So the machine learning approach in these identified signals, the noise was labeled out beforehand, I should add, for that example. So these are just a handful of some of the applications people have used in geosciences, but there are lots of others to explore. And I will still say that machine learning in geosciences is still somewhat new. So I encourage everyone to apply it to your own research so we can have a robust set of tools out there for all of our disposal. So I'm going to pass it to Grace now to get into more detail about starting machine learning from scratch.
Yeah, so we have learned what is machine learning in general and heard about its great application in geoscience. But the following question would be, how can we apply this tool to your own research? In other words, how can we start a machine learning project from scratch? And can everyone do it or no? So in the following slides, I will go through 6 steps, and then that help you hopefully start your own machine learning project in the end. Like every project, we always need to identify a goal as a starting point. First, we need to know what are the issues in your field that you are trying to answer. How are the current problems being solved? And is there any limitations of the current method due to like constraint of the space or time? If you are dealing with a hyperdimensional data set, maybe manually trying to find the connection between each parameter will cost a lot of time, and you will prefer to have an algorithm that can speed up the process. Due to those complaints, maybe you want to incorporate machine learning as a project or tool to help you achieve a better result. That will be predict the next data point in your time series initial data set, or trying to improve the current efficiency of how you process your data, etc. Asking those questions are essential for us to compile our data sets and also configure our machine learning model. Machine learning usually requires a larger amount of data set in order to achieve a high quality result. So data choice becomes one of the most important things. Do you want to use existing data sets from any database? Or do you want to use experimental data sets? Do you want to simply collect more data from the laboratory or go to the field, or asking collaboration from different institutions? If none of those approaches work, do you want to synthesize more data via simulation? The quality of the data determines the quality of your result. Like we have mentioned before and emphasized throughout this series multiple times, machine learning is not a magic box. The quality of the data really will reflect on the quality of your output result. So if there are certain bias in your initial data set, you may need to think about them, identify them when you interpret your result. Is there any observational bias or sampling bias from your initial data set? Will that be influential on your output value? Once you have your collection of data, the next step is to think about how to formalize those data. And we call them pre-processing data sets. Do you want to standardize or reshaping your data to the same format? For example, if you're dealing with geochemical data, like what I usually deal with, you may encounter majority of the data appear as a log normal distribution. Do you want to normalize your data distribution into Gaussian first? If you are handling imaging data sets, do you want to make sure all the imaging are having the same size and a pixel? If you are doing time series data, do you want to make sure all of them have the same data point and the same time span? This step is very important to ensure the patterns that we learned are the result of the data, not the format difference. Once the data has been standardized, you also need to think about how do you want to read in your data and how do you want to export your data. And those are important questions because it usually depends on the goal of your research project. If you just want to simply classify your image or your chemical data, maybe your export results just be yes and a no, a binary answer. But if you want to predict the next data point in your time series, you may want to configure your data or model differently. how you want to organize your data once you thought about the previous two questions. Do you want to keep all your data in the same folder, or you want to extract data from different folders and load into your machine learning model separately? Do you want to label your data as a part of the folder name so that will facilitate your loading process? Once all this initial step has been processed, the next step is to choose the correct or most appropriate machine learning model or neural net that you want to start with. Here, I'm showing you a fully connected feed-forward neural net, one of the most popular neural nets that we use in many research. And like many neural nets that we have, it comprises of three fundamental layers: the input, hidden layers, and output. Just by its name, so the input is where the input data set goes through. The output is where your results being generated. The hidden layers is where the transformative algorithm going on that can process your input data and generate useful or meaningful prediction for your output. The fundamental unit for each layer is what we refer as neuron. The neurons in successive layers, for example, between the input and the hidden layers, they are connected by weight. So think about these as neurons in your brain, right? The dendritic connection between neurons, if they are very strong, there will be a stronger response to any external stimuli. In the machine learning world, if the weights between neurons are very strong, your results will be more biased by that certain input value. Here, the reason this is a fully connected feed-forward neural net. The fully connected means that all neurons are connected between the successive layers, as illustrated by this example. Feed-forward means that the data always go from one direction, from left to right, from input to output. The actual structure of a neural net can be very diverse. You don't have to be limited to a single hidden layers, and you don't have to limit to a 3 neurons input layers or 2 neurons output layers. The connection between neurons doesn't have to be fully connected all the time. As you can see, there are many examples they're only connected by once. Data doesn't have to always go through from the left to right. Sometimes data, the input value will generate in the neuron and go through them recursively in order to reinforce the process. The function of the choice of a neural net is very important for your research goal. For example, if you are dealing with time series prediction, long short-term memory, LSTM, may be the best neural net model for you. And if you want to learn more about different neural networks and how to apply them to your specific scientific question, come to Machine Learning Club, and we will talk more about it. So we know the general architecture about how machine learning model is, but the following question is, what is the math behind it? How we can actually convert all the input value into a meaningful output value? What are the simple logic behind it? So we can imagine we load our data into our first layer, and each data was encoded by a certain value. The first neuron in your second layer or your hidden layer will be a result of certain step function of all the weighted sum from your previous layer, plus a certain bias. And if this value is greater than a threshold value, your neuron will be activated. On the other hand, if it is lower than your threshold value, the neuron will be discarded, and you won't produce them or use them in the following layer calculation. We usually refer this step function, Gx, as an activation function. And then there are multiple different types of activation functions that can be usable for different applications. In most of the time, when the most popular activation function for the hidden layer that we use is ReLU, which constrains the input value that you put into in your step function from only positive value. You will automatically let all the negative value to become 0. So as you can see from the chart, any output value can only from 0 to any input value that you have, only the positive value. Choice of activation function is one of the parameters that can actually adjust your model performance, which we will talk about later more. But if you want to learn more about how to choose activation functions and use them, again, come to Machine Learning Club, and we will talk about more. So we repeat the similar process, calculate the weighted sum of previous layer, and then determine a step function, and apply it with a step function to determine whether we want to turn on or off of our output neuron. Of neurons in the output layers. If the neuron is actually effective or is actually on, then we try to calculate a certain probability, which gives us the confidence level of our prediction based on the input data and their weights. So we have to know the very basic concept about how the math and how the model work. The following question will be, okay, how do I load my data into the model? Like I've mentioned before, all the data needs to be standardized and labeled. Once you have that initial data set, the first step is to divide your initial data set into 3 different categories. And then they are training, validation, and then testing. For the purpose of training, which is to understand the best weight and the bias in your machine learning model, we only focus on training and the validation data set. We will talk about testing data set later. So how does this work? We select a batch of data from your training data set, and we load it. We assign some arbitrary weight and bias initially in our hidden layers. And then we generate some arbitrary output values. What we do next is to compare the output values with the data label of our training data. And we try to evaluate what are the difference, or what we refer as cost of our prediction and the data label. If they're really different, we will then go back and try to adjust the weight and the bias of our hidden layers. And we refer this process as back propagation. We repeat this process with different batch of data that been pulling out from our training data set. We usually shuffle them in order to make sure we have enough batches of material that we want. Once all the training data set has been seen by the model, we say one single epoch of training is finished, and our weight and the bias are somewhat been set. The next step is we try to understand what are the current performance of our model. So what we do next is actually to load in our validation data set. We repeat the same process, feed through all the validation data sets with the weight and the bias, and then trying to get and compare them with validation data model, data label. And then we will evaluate our result with model evaluation matrix, such as accuracy or root mean squares, or etc. Depends on different output value that you actually have. And this will be the temporal evaluation of your model at the end of a single epoch. For the entire training process, you have the choice to choose as many epochs as you want. And actually, that's one of the hyperparameters that you can adjust in order to tune your model to their best performance. And here we alluded to model optimization. There are actually many other parameters that you can choose. For example, the type of the model, the number of neurons in your model, the number of hidden layers in your model. All of those parameters can be adjusted in order to achieve a desired result. Similar things include activation function, how many batch of material you want to introduce in a single set in your training, and how many epochs you want to change. Other fancy techniques include regularization methods. For example, you don't have to use all the neurons all the time in your layers. You can randomly turn off or turn on certain neurons as you go through your training. And then that process is referred as dropout, which we will use in the following tutorial. You can also normalize your data or output data in the intermediate layers, so that when they introduce to the next layers, you also always get ideal result. Finally, after your training process has been finished, which means your weight and the bias of the model are set. Now remember, we still have another set of the data. They have never been seen by your model. And that's our testing data set. What we do is to finally try to evaluate the model performance. We will introduce the testing data, and we will repeat the same process, evaluate them with the similar model matrix, and then try to understand how my model currently works and how generalized my model is. And then so I have talked about different concepts that can be used in order to apply to help you to initiate a machine learning project and then to make sure you obtain some meaningful results. And then in order to enhance those concepts, I will let Heidi to give you a tutorial about including some interactive coding about how we can practice them with a specific problem. So Heidi, go ahead.
Okay, so this is where we get a little more hands-on approach, and I think it'll be more instructive for everyone to go through this process together. So to motivate our very simple example, we're going to try and train a convolutional neural network to correctly label these 6 different rock types correctly. And this could be obviously a really pertinent example for some of us in this room who might have image-based data. But the general idea here is that we want to be able to label these 6 different rock types, and the data set consists of high resolution close-up images of hand samples of each of these 6 types. Okay, next slide. And so what we're going to do is, this is the general architecture that we're working with. And so we have our input image. So the close-up image of a hand sample of these 6 different types is going to be fed into the first convolution layer. And these convolutions, you can sort of think of them as taking a magnifying glass of a certain height and width and scanning over your image to extract dominant features from it and summarize those dominant features. So we'll go through these convolutions, or sort of scanning over the image and summarizing any dominant features, and we'll pull together the results. So we'll summarize those, and it'll go through a couple sequences like that. And finally, once we have these summarized sections of what are the dominant features of these images, we're going to actually squash down the data into a vector form and feed it through these fully connected layers, which is what Grace just walked through. So this multi-layer perceptron style feed forward fully connected layer. So we're first going to do the convolution, then we're going to utilize the power of these fully connected layers to try and classify each of the images into one of the 6 output options here. So this is the general idea of what we're doing. And so now I'm going to paste in the chat, and I did before as well, the collab notebook that everyone can go to. And I will share my screen. Okay, does everyone see the collab notebook okay? All right, so for those who haven't used Google Colab before, this is essentially a notebook environment where you can code out Python and use Google servers instead of your own. So if you have a sad, slow computer, this is a nice way to overcome some of the limitations there. So what I encourage everyone to do is to open up this notebook. And in order to make this more effective and make sure that you can actually edit it and play with the hyperparameters and see if you can get a really nice, accurate model, you'll click File, you'll save a copy in your drive, and then you'll work in that copy so that you can actually edit some of these hyperparameters. So you can name it whatever you want, but I'm just going to rename mine because I hate seeing the words copy of when I'm looking at my drive. Okay, so we have an introduction here, which is what I just went through in the slides. And the thing to really keep in mind when you're working in Collaboratory is that when you have these code blocks, at least for this case, you're going to want to run these in sequence, and you're going to want to wait until the previous code block has finished running before you proceed. Just saying that for organization purposes as you follow along. But the first thing we're going to do is mount the Colab notebook to your own drive. So if you're using Chrome and you're already signed in, this should be a fairly smooth process. Otherwise, you might have an extra step of signing into your Google account. But you'll see this link to pop up where you'll sign in and create an authorization code for yourself. So as usual, Google wants everything from you. If you're comfortable sharing all these things with Google, you can click Allow, and it'll generate this code for you, this activation code. So you'll copy that and head back over to your Colab notebook and enter it. This will allow you to store files temporarily in your drive or permanently in your drive to make this run a little smoother. Okay, so moving on to the next code block, once you have the message that it's mounted at your drive. The libraries that we're going to use include TensorFlow, Keras, scikit-learn, and a few others, which are all beautiful libraries that allow you to do a lot of sophisticated coding without having to actually get down to the Python-based code. So you'll want to click Run on this, and if it's running efficiently, some of these are for plotting, some of these are for the actual machine learning architecture creation. What you'll see is that all of these will load through and download, and we're just going to wait until we get the message that this is done.
Can I ask a question, Heidi?
Of course, yes.
So just tell me about the architecture, what's happening. So there's some download happening. So this is coming to your local computer?
So it's actually running in Google's.
It's all in the cloud.
It is, yeah. It's all on Google's GPU.
So downloading from some centralized Google server to your local drive, but it's all still in the cloud.
Correct. Yeah, it makes it really powerful and nice for when you're playing around, especially with large data sets and maybe don't have the.
What do we think Google is doing with all this data?
I shudder to think about that.
What are they? They're an advertising company, right? So I'm just kind of curious what they're doing with rock data. But anyway.
So this is actually, the rock data set is on Kaggle. So we have it on Kaggle that you'll load into here. It wasn't native to Google. So next, mentioning Kaggle. So we will link into Kaggle and make a directory for that so we can pull in the Kaggle data set of all of the images. Then we created a token so that this can just be easy for everyone to point directly to the Kaggle data set. And we will link here. So if you get this error, for the life of me, I don't know why it does this, but sometimes you have to import the key twice. And then typically the second time you do this, now it's happy. So after this, you'll get this warning that it's readable by other users. And to fix that, we are going to do this code here, this chmod 600. All right, so now we are ready to load in your data set from Kaggle. So if you find other data sets in Kaggle and you want to use this as a base code, feel free. You just need to point it to the right address. So in this case, we have the data set at kaggle.com/Heidi Myers/rock classification. So we will click play here and it will download the data in. Okay, next step is to unzip it. And you'll see this inflating message here as it's downloading all of the images. Okay, so there's 30,000 of them. So it still doesn't take that long. To double check that you actually have the data set loaded in, when you click the folder icon here, you should now see a rock classification directory. And if you expand that, you'll see that there's 3 subfolders for test, train, and validate. And if you expand further, each one of these have the 6 folders for each of the 6 rock types. So this is how we're labeling this data set. We're using the folder headers as the label, as opposed to doing something like having an Excel sheet with the file name in one column and the label in the other, which is another straightforward and popular way to do your data labeling. Okay, so we're just gonna do this out. So now we have the folder available on our drive and we want to load it in. So what we're going to do is point to each of those folders as the training data directory, validation data directory, and test data directory, and note how many samples are in each folder. Of course, you could always just write a little script to traverse the length of the folders if you don't know how many files are in each folder beforehand. So we'll go ahead and do that. And now if your images weren't already 28 by 28 pixels, this would be one way to change the size to make everything standard. In our case, they already were 28 by 28, so these teeny tiny little pictures. But we want to note the image width and height. And just to give an idea of what these look like and have a peek into the data set, I'm going to pull the first images from each of the folders in the training data set. And again, since these are 28 by 28 pixels, even at this size, it's going to appear sort of smeared, but you can see that these are color photos for each of them. And some texture features you can probably even identify this small, but just to give an idea of what our input data is. So here's that architecture again. So now's the point where we're going to actually translate this architecture that we've thought about into code heavily using Keras libraries. So there's a description here about all the different things you can change and what these commands mean that I encourage everyone to go through. But for the sake of time, we're just going to really talk about the code instead. So you'll click play here to start building your model. And this set is just in case you have images that have channels, however many channels are in it listed first when the image is read in or last. Sometimes if you're dealing with these, something as simple as having the channels listed first or last and having a mixture of the two can be confusing and spit out all sorts of errors. So make sure if you do know beforehand, you can just set the input shape with that. And if you don't know beforehand, you can just put this code block instead. So we're going to be using the sequential library from Keras, which allows the building of the architecture in a sequential format, as you might imagine from the name. And so we're going to hit our first convolution layer. And so of those filters that we talked about, the convolution filters, the first layer is going to have 32 of them. And so the kernel size, or in other words, sort of the dimensions of that magnifying glass that goes across the image and scans, is going to be 5 pixels by 5 pixels. We're going to use the ReLU activation function that Grace mentioned is quite popular. And when all of that information is summarized, we want to summarize all of those features into a 2 by 2 structure instead, so 2 pixels by 2 pixels. So that's we're going to take the maximum of all of those dominant features that were summarized throughout this convolution. It's going to go through another convolution next, and this time we're going to use 48 convolution filters. We're going to use a smaller magnifying glass, 3 pixels by 3 pixels. And we're going to still use our ReLU activation and summarize the information into a 2 by 2 matrix instead. At that point, we want to start feeding into our fully connected layers, so that sort of feed-forward neural network that Grace described in detail. So to do that, we need to flatten this high-dimensional data into a vector form. So Keras is beautiful that you can just say flatten and it'll do that for you. And feed it into the first hidden layer. In this case, the first hidden layer is going to have 64 neurons, 64 nodes. This is another one of those hyperparameters that you can tune and play around with and add or subtract neurons to see how it performs. We're still going to use ReLU activation. And in this case, we're going to add some dropout of 10% of the neurons for regularization purposes. After that point, it's going to go into the second hidden layer. This time it's going to have 32 neurons, still going to be activated with the ReLU function and still with 10% of the neurons turning on or off, until finally you get to the output layer. And so why might there be 6 neurons in the output layer?
I know.
You don't count, or you do.
Fine.
Anyone can shout it out.
I don't count either.
So if you'll recall, we have 6 different rock types that we're trying to classify. So your output should have as many neurons as there are different categories that you're trying to classify. And the trick here too to remember is if you're doing a binary classification, then you really only need 1 neuron, because if it's on, it means something, and if it's off, it means the other. So that's why there are 6 in the output.
So in the interest of just healthy skepticism, what would happen if you chose 5 or 7?
I think you would.
Does it break the problem?
I think it breaks the code, really. So I think if you have fewer categories than there are classes that it identifies during the process, it's going to send an error that there are more neurons than there are classes available.
But isn't it possible that a reasonable algorithm might say, well, you know, these look really, really similar, so I'm going to call them just one classification. And I really can't tell the difference between, say, gneiss and granite. I made that up, but you get the idea.
So the way that I understand that how these work is, so at least the way that this is written, so it flows through the directory to figure out how many classes there are in your input data to begin with. And because it's going to read that there's 6 different folders with 6 different labels, there wouldn't be a mismatch. But that's actually a very good question. If I just say 5, what sort of message am I going to get? Which, yeah, let's play around with that, but let's do it after the demonstration. Or Ved, do you have insight?
If I can make a comment, this is not a model selection problem. This is a kind of a parameter estimation problem, right? So we're not asking the machine, we're not asking this neural net to tell us how many classes there are. We're telling it how many classes there are and asking it to classify. So I think you could reformulate it in some way for it to give you how many classes it thinks there are. But what happens in practice is that when there's classes that are indistinguishable, it just, the performance reflects that. And I think Heidi will show that.
Split. Yeah. So that's more about like the clustering sort of approach. But okay, thank you. Go on.
Yeah, which is a different. Sorry.
So is it forced to make a decision when it really can't decide? You're still forcing it to say it's in this bucket or this bucket. It's not a I can't work it out bucket. It
is. Yeah. Okay. So you set the threshold value above which you say, okay, it has to be this. Each of those individual neurons has to be either on or off. So it's that's sort of how it's.
Hey Heidi, just a quick comment. I think it'll be very beneficial for all of the audience here if you briefly, share the comment where this is actually the sort of the approach where you actually have these labels items in advance. I think how Grace also put it out is, this is like a whole like a machine learning overview, and that kind of a fair judgment. I think it's also fair to introduce some sort of an unsupervised learning approaches where you don't know what to look for in the data set, and I think that will sort of clarify the questions here.
Yeah. So the purpose of this seminar is really to sort of get people excited about talking about this and introduce an example where we have labeled data, which actually the lack of large labeled data sets is sort of a hindrance to applying machine learning to geosciences in general. And so I actually hope that this will encourage people to join machine learning clubs so that we can talk about unsupervised learning techniques, which of course are a beast of their own. And I think that actually would be more useful for those who are trying to use machine learning for exploratory purposes rather than classification purposes.
Yes, and then we are trying to make use of the time and make sure it's within 1 hour. So that's why we want to really emphasize on one specific part of it and then extend this workshop throughout to different machine learning club meetings so that we can talk about different applications in the future. And then, yeah, Heidi.
Okay, So once we've built that model, you can see that the total number of trainable parameters is quite large, so 169,174 for what we've built. And so now we want to actually train the model. So this is the point where you're going to say how many times that model is going to be able to look at the whole data set, so how many epochs it's really allowed to go through, and how many images it's going to pull at a time when trying to learn what these dominant patterns are. And I'm going to hit play before I start talking about this because it takes a little while to run this. So we've set our epochs. I encourage everyone in your copy at a later time perhaps to comment out the 10 epochs and to uncomment 30 and try different numbers of these to see how the performance is different. So in this case, we're going to use the flow from directory labeling structure, as I mentioned before. So it's going to see what the folder name is and use that as its label. So in order to do that, you use the flow from directory command from Keras. And we point for the training generator, we're going to point to the training data directory, tell it what the image size should be for the input image, let it know that it's looking at 3 channels for each image, give the batch size, let it know that it's sparse for the class mode, and we're not going to shuffle. So we're just going to grab these. You have the ability to shuffle in between epochs. And same thing for the validation generator, except pointing to the validation data directory. Everything else is the same within these. And finally, to fit the model, we're going to use the training generator. We're going to go through each of the epochs. And then for each epoch, we're going to use some of the validation data to evaluate the performance of the model at that point. And so there's a beautiful website service called WandB or WNB that if you already know how to use it, you can just uncomment this section of the code. But it's a lovely way to keep track of your training your model and having good visualizations of its performance. And you really get a visual idea of how it's learning. And if you want to learn how to do that, this whole thing is becoming a big advertisement for Machine Learning Club, but please feel free to join us to discuss that more. It'll be quite helpful as you're learning to, or as you're applying this to your own research. So as you can see, this is why I pressed play before starting to walk through what the code is. It takes a little while to run this particular one, but what you'll see is as it goes through each epoch, you're going to see 4 different metrics that display. You're going to see accuracy, loss, validation loss, and validation accuracy. And first off, you might wonder why there's 443 steps to this. Well, we set a batch size of 46. And so with batch sizes of 46, in order to cover the entire training data set, it needs to go through 443 times. So 443 times 46 is the number of files that are in the training folder. So what these first 2 are asking the question of how well does the model match the training data? How well is it able to label the data correctly of just the training data set? And the second 2 values are asking how well does it generalize? So from the validation data set, once it sets the weights and biases based on the training data, let's shove the validation data through and see how it performs. So as you might imagine, the simplest first guess to start is that everything is equally probable. If something is completely dumb, it doesn't necessarily know how likely it is for something to be an andesite or a rhyolite or a gneiss or so on and so forth. So this actually falls pretty closely to just guessing that everything's about equally probable for 6 different categories. So it starts off on the first epoch of having 18.15% accuracy. And when it tries to generalize, it actually generalizes a little better at starting with 31.35% accuracy. And what you should see if your model is learning and if your model is adapting as it's taking different chunks of the validation data, different of the training data, and then testing it against the validation, is that the losses should go down after each epoch and the accuracy should go up. So as you can see, we're on epoch 7 of 10, and our losses after each epoch are generally going down. Accuracy is generally going up, and same thing with validation, with the exception of this epoch here. is generally going down and accuracies are generally going up. And you can see how quickly it's really learning. So by epoch 5, it's already predicting with 94.05% accuracy from the validation data set. And once this goes through, we'll plot to have a closer look. But yeah, that's, I think while we're finishing the last 2 epochs, I see there's a lot of comments in the chat. Perhaps there's a question or two I can address. Or Mike, you have your hand up? Did you have a question?
Yeah, if I may. The question was, are these are skill metrics? They're all measured on the validation set?
So they're measured at both the training set and the validation. So the training metrics really tell you how well the model actually predicts from the data that it used to build the model.
Yeah.
And then it looks at separate data and asks how well it generalized. So when it gives an opportunity to learn and adjust those weights and biases based off of these metrics when it's still in the training.
So you want kind of a balance between model complexity and validation skill, right? I mean, you don't want to describe every last nook and cranny of the training set, but then completely fail to do so when you test that model on an independent data set, right? That's the idea of validation. So I'm wondering, what's the strategy for avoiding what we call artificial skill, which is what I kind of just described, that phenomena? Because when you start with a validation data set that's just a fraction of the size of the calibration data set, you kind of tilt the odds toward doing that.
So it sounds like that's sort of, from my understanding, that's overfitting, what we call overfitting in machine learning. And so overfitting, the ways to overcome something like that is to introduce regularization and normalization. So these regularizations sort of push the model to keep learning when it stalls out, or can punish the model if it does something inaccurate once it gets to looking at the validation training set. So really the way to prevent overfitting is to tune your hyperparameters and ensure that there's sufficient regularization to overcome overfitting. I hope that helps.
Yeah, and then the question is, how do you tune those hyperparameters?
So
do you
yeah,
just choose things, or is there some kind of a objective way to do it? So there's another whole class of ideas called information criteria, where there's this balance between calibration or explanation by the training and model and reduction in the validated accuracy, I guess.
Yeah.
So a simple experiment I was suggesting in the chat was simply to swap your calibration and validation data sets and see whether you should get the same result as PMP, who I'm not sure that actually is. So,
that's Phil.
Phil M. Piccoli, right? Phil Piccoli, yeah. Anyway,
Thanks,
so yeah. So I wonder, that's something we often do in like non-machine learning contexts, is just swap the training and the validation, or just randomly sample to get realizations, which I suspect is happening here. But.
Yeah, that is part of where the validation set pulls from the validation folder is sort of random. You set the batch size and it pulls chunks essentially of the validation set. But yeah, as far as I can see, there's not a sort of standard way to go about tuning your hyperparameters, or at least for this sort of context. It's sort of trial and error. Although with powerful things like WandB, you can set it to do a whole bunch of different hyperparameters to try out, and then figure out which one has the best model performance to then base your code on. So yeah, it's a very powerful tool for anyone who is working with machine learning. If you're not already using it, you should.
Heidi, can I ask a quick question? When you're preparing this particular example for today's talk, for how many hidden layers to be and all these hyperparameters that you were just mentioning, how did you select? Are these optimized? Or was this something that you just randomly selected and it worked really well? Or I'm just interested how you actually did that. So
for this one, I actually used the same convolutional neural network that I made for my unidentified or unexploded ordnance studies. So I created that one, optimized it, and then I just wanted to see how this entirely different data set would perform using the same one. So there's absolutely room for optimizing within this, this architecture, and I encourage people to play around with it and see how accurate you can get. And for the sake of time, I chose the fewer number of epochs, but there's undoubtedly a better version of this to play with. But yeah, it was something I already built. So
cool. Thank you. Thanks for the insight.
And just to add to that, I mean, in terms of design, there are, yeah, Heidi's totally right that, you know, you can kind of like tailor your design to a particular problem, but there's also a little bit of like standard kind of design. So, you know, a couple of fully connected layers, a couple of convolutional layers, and everything is kind of variation on a theme. Back in the day when people were first doing this stuff, they would have these like totally crazy, like I have 27 layers, like super deep design. And I don't know, I kind of don't see that quite as much anymore. It doesn't seem like it's totally necessary, unless you're trying to get like ascension behavior.
True. Since we're getting close to the 1 hour mark, I'm just going to go ahead and go through the last couple plots, which just are going to summarize how the model performed and use the test data to just have another way to make sure or to ask the question of how robust this model is. So we ended up with a validation accuracy of 96.47 at the end of our 10 epochs. So you can see even with 10 epochs, it does pretty well with being able to distinguish the 6 different types of rock images that are input. So let's just plot up. So we saw generally that the loss was going down and accuracy was going up, but to be more precise, so this is really kind of what you want to see when you're training, when you're going through the machine learning process. You want to see your losses go down. You want to see your accuracy go up, and you can see that there is some jitter, especially for the validation accuracy. So there's absolutely room for improvement in this architecture, and I would love to see what people come up with using this for the base. I'd love to learn too what other people think is useful. Okay, so now we're going to look at the test data set. Now remember that during the training process, for each epoch, once it got to the validation part, it was grabbing from your validation folder. So one might be skeptical and say that, oh, well, any of these metrics, it's already seen that data at some point. So how are you really evaluating how robust your model is? So now we're going to look at the test data the test folders, which it's never seen in the training process. So your weights and biases are set, your architecture is set, and we're just going to feed in some new to the model data. So similar process of creating our test folder generator. And now we're just going to create a confusion matrix to compare what the model classifies the image as versus what it actually is. So in this case, just for demonstration purposes, we already have the labels beforehand of what these images are. So we're really seeing how well the model generalizes before trying to just unleash it on some new data. Say, oh, now I can fire the people that I had that were classifying rocks based on images and use the machine learning code instead, which we don't want. So when we do that, we get these different metrics. And in this classification report, you can see what the precision values and recall values are subdivided into each of those 6 rock categories. So 1 is perfect, anything less is less than perfect. And for those of you who like to think in numbers and get a lot of information from numbers, I applaud you, but I'm also going to put a plot here because it's easier for me to conceptualize that way. So we're just going to plot up this confusion matrix, and I'm going to zoom in so people can hopefully see this a little clearer. That's a little blurry. But when we use the test set, the model that was already built was accurate 95.5% of the time. And what this confusion matrix shows is on the x-axis here are our 6 categories. And so these are the labels that the model gives the image. This is what it thinks the image is. And on the y-axis are the true labels, the ground truth. And so if it were perfect, if this model were 100% accurate, all you would see would be values along the diagonal, and you'd see zeros in any of the off-diagonal positions. And if you see something like that, again, you'd be highly suspicious of any model that claims to be perfect. But this helps give insight into which images are confusing, and you might be able to redesign the architecture of your model in order to overcome some of the confusing parts. So in the case of this model, the thing that is most often confusing is labeling andesite when really it's quartzite. That happened 44 times out of the 3,600 sample or input images. 34 of those were confusing gneiss with schist, which I too confuse gneiss with schist. So that might be harder to overcome in your model architecture. And sometimes and here it's on the opposite side of it. So it predicted schist and it really is gneiss. So this can help give you some insight, like I said, into restructuring your architecture, playing around with your hyperparameters, informing how you're going to play with your hyperparameters, and really help you make the best model that you can. And so I'm going to leave this with a challenge. So we achieved 95.5% accuracy today. When I tune the hyperparameters, can get 98% accuracy. If you can beat me and come to Machine Learning Club on Tuesday the 23rd with higher accuracy than 98%, then we are going to give you a Starbucks gift card. So, please come to Machine Learning Club.
Yes.
Hey, I would sponsor a future prize. Just contact me offline.
Okay, awesome. So yeah, I look forward to looking through the comments here. It seems like there is a lot of interest and questions with this, but perhaps we can open the floor for questions. If people have time to stick around, that's great. But if you need to drop out, of course, we understand. But yeah, come to Machine Learning Club.
And we can learn together.
Sorry, when do you guys meet? Is it regular or?
So we meet Tuesdays at 2, and I'm going to drop in the chat right now our website, and there's a Join Us tab on there. If you put your email in, we'll send you the Zoom invite.
Okay, I may sign up, but I'm not sure.
No one is obligated to come all the time.
But it sounds like fun. Thank you for doing this.
Of course, yeah. And we have a Slack channel for the Machine Learning Club if people are interested, but that time doesn't work. We can always re-poll and find a better time for everyone.
Yeah, and the purpose is actually for us to really exchange our ideas and think about potential projects. How can we apply machine learning concept into our current project, and also practice our coding skills, because we are actually learning how to do this machine learning architecture into different coding platform. So now for the demonstration and then for interactive purpose, we use Collaboratory, but most of the time we will use Spider. So we will have less problem. Actually, for all the loading data set step, it will be less tedious as showing here. So if you join Machine Learning Club, we can all grow together with those. Questions? Okay, that's perfect. Or you can just email Heidi and I, and we can talk offline more.
I think I was telling Ved at the graduate student open house that we have some local resources, new local resources, and he was kind of poo-pooing it as like tiny, but they're available to play with if you want.
I was not poo-pooing it. I was saying it's a great place to like get your codes up and running.
You can poo-poo, it's okay.
But I wasn't. You misunderstood. However, your GigaPan idea is fantastic.
Yeah.
Well, and the other thing I was thinking was like I think Heidi was getting to this at the very end, which is like, can you train your model and then apply it to something completely different? And so this is something like Grace is thinking of doing, right? Like train your model on Earth, and then like set it loose on Mars, and do with some confidence that you believe it. And so of course, what do? You try it out on other places and completely independent sets that were not part of training or validation. So it's like application, I guess you would call it.
Yeah, that's actually a process called transfer learning, and it is currently being used for people to classify rock image on Mars. And then what we are doing here right now is actually trying to be used in order to classify rocks based on image that we saw from Perseverance or Curiosity trying to classify Martian rocks by just using the rock image from Earth. So it is something that people use.
Well, in the case of the gigapan idea, like it could be like, Jay has like a Neoproterozoic sequence, gigapan, right, from someplace in the world, and he uses it to identify like characteristic features, and then so you train the model, and then you set the model loose on a completely different gigapan image from a different location, like type locality, but which is still potentially like maybe it's a proposed Neoproterozoic period, and then you see to what extent it's likely that everything matches. And there's
a really fun application.
Those files are like, they're enormous, huge piles of data, and so you could imagine. I can't imagine how many little JPEGs you would get out of one of them. Probably a lot. Yes, let's keep it in mind in case there's an undergraduate who wants to do a project like this.
Yeah, that would be a fun one to code.
Thank you for this. Didn't mean to keep you over time, but it's fun.
Thank you. So it's already 8 minutes past 1, and we can always continue our conversation offline. And thank you everyone for coming today's workshop. I think everyone, at least we make some people get excited, right? For the gift cards, right? Free gift card, at least that part. So thank you so much for coming. And is there any words that Heidi wants? Sorry, did I interrupt someone?
So, no, yeah, I would just thank you everyone for coming, and I hope that this inspires you all to play a little with machine learning. And for those of you who already are, I would love to hear about it and learn from all of you.
Yeah. All right. Thank you.
Yep. Thanks.